So I just talked about the possibility that escaping the Earth, getting swallowed up by the sun and arrive somewhere else. Then of course we need to know that there are newer stars and newer planets we can possibly live on. Fortunately, we do see that new stars are born in our Milky Way galaxy, for example, like right here. So what is happening there is that there's a cloud of gas, and you actually accumulate this gas, which is basically made of a bunch of tiny little particles made of atoms, of course, and eventually they coalesce into a formation of a star, and there will be a dust around it, which eventually forms rocky planets like the Earth. So it's an interesting subject of research these days if you can ever find extrasolar planets. For a long time, we knew of planets only inside our solar system. Now here's an explosion. New observations have identified candidates of planets outside the solar system, and this is the part of the way it was actually earlier this year. And there are more than 2,000 candidates of extrasolar planets. And you see the distribution in their masses. So some of them are very heavy, like Jupiter. Some of them are much lighter, and Earth-like planets. So what you see here is that bigger ones are easier to spot. So it tends to find bigger ones. But down here, you also find the candidates of planets which are sort of a similar mass as the Earth. And some of them also happen to be sort of the right distance from its star, that the temperature is right to have liquid water, which we mostly think that it's necessary for the biological systems to develop. So there are candidates of planets outside the solar system which can possibly support life. And this is a very interesting subject of research today. And in this picture here, this is the first ever picture of a planet outside the solar system. And the star is so bright compared to planets, because the planets don't light up on their own, that they actually manage to mask the star itself. So you try not to see the star by a mask. Of course, there's some residual light coming out. But then you look slightly off direction, you find the candidates of these planets. So this is the first ever picture of planets taken by a telescope called Subaru telescope, built by Japanese National Astronomical Observatory on the the big island of Hawaii. So summing this story up, the stars would come to an end, and the bigger the star is, they will live shorter. So that's another life lesson, if you like, to draw from it. The bigger star would end up with a big explosion, and that would let all the outside part of the star just fly apart, and there remains the core. And if the star is big enough, the core turns into a black hole. We talked about that. If it's slightly lighter, it doesn't go all the way to form a black hole, but leaves some very, very tiny, dense core called neutron stars. So in that case, the entire star becomes only as big as like 10 kilometers, and the entire star is basically like a big atomic nucleus. So that's the neutron star. And if the star is lighter, like in the case of our own sun, again, it does blow up, and it leaves this very dense core, but not as dense as a neutron star. And these objects are called white dwarfs. So depending on how massive the star is, they have different lifetimes, and they have different things to end up with. But the most important thing for our discussion here today is that the stars form bigger and bigger chemical elements. The sun burns hydrogen to build helium. And that can happen even in a fairly smallish star like the sun. The hydrogen can go to helium. In the case of the sun, it can probably go all the way up to carbon. It will bring in 3 helium nuclei together, fuse them into carbon. That is going to happen in the sun as well after it comes very close to the end of its life when it runs out of the hydrogen fuel. But it's believed that it doesn't go any beyond that. You need much bigger and more massive stars to let the reaction go further by going from carbon to neon and silicon and iron. So you can keep building up heavier and bigger elements by using the inner core of bigger stars. And if you take some example of a typical star which goes all the way down to iron, the time scale is actually not that long. Hydrogen burning may last only like 7 million years, and then things start to getting faster and faster. Helium burning into carbon, to neon, oxygen, silicon. At the end of the day, silicon burning may last only 1 day, and then comes to a dead end. Once it comes all the way to iron, it cannot go any further beyond that. And that's simply based on energy conservation. So as I said, by putting them together, you're actually releasing mass. And that's the way energy comes out from these processes. But once it comes to the bottom in this energy curve, so this curve is showing that it's sort of like a hill. If you start from hydrogen, then it's sort of the top of the hill, and can keep rolling down the hill, eventually settle down where the minimum is, and that actually turns out to be iron. If you want to go beyond iron, then instead of releasing energy by shedding mass, you need to put energy in to make the reaction happen. So that doesn't happen inside the sun or any stars as far as we're concerned. So this is the dead end. Once it comes to iron core, then it cannot do any more nuclear fusion process to release more energy to support its weight. Then it would collapse. And then bang, that will lead to an explosion of the star. So this is the picture of an explosion of star at the end of lifetime in a large Magellanic Cloud. That's sort of a companion small galaxy nearby, like 160,000 light years away from us. That's our neighbor, as you have learned in the previous lecture. And this explosion also caused a lot of neutrinos to come out. As a matter of fact, even though this is a very, very big explosion, you could see by almost naked eye, and you can see that this explosion emits light almost comparable to the entire galaxy of Large Magellanic Cloud. Actually, 99% of the energy is released in the form of neutrinos. Only 1% is something you observe in terms of light. So tons of neutrinos are released, and after the travel of 160,000 years, they reached another water tank called Kamiokande, and that happened in 1987. And because the neutrino is so difficult to detect, most of the time you're worried about noise. What you see in this picture here is as a function of time. Most of the time, all you are seeing is this noise. That's not something you want. It's just a noise. But on one moment, you see here's a big burst. A lot of neutrons came very closely bunched together in time, almost at an instant, within 10 seconds or so. Clearly, this is not the noise. Noise wouldn't do this. So something explosive has happened. And it turned out, after astronomers looked for a exploding star, they found this. So this burst of neutrinos came from the explosion of this supernova. And that led to an award of Nobel Prize in Physics to Mr. Koshiba. And that was, of course, a very, very big event and an important discovery. And one of the reasons why this is so impressive is that just even a month before this discovery, this experiment has so much noise, they couldn't have possibly detected neutrinos from this stellar explosion. So they were lucky that this happened a month after they became ready. But a month later, Mr. Koshiba had a mandatory retirement from the university. So there was only this 2-month window when he could have possibly detected neutrinos. And so exactly at the middle of this 2-month window, and 160,000 years earlier, the stars exploded so that neutrinos could be seen by this experiment. So one thing you learn from this lesson here is that you got to be very, very lucky to be successful in science. So remember that. But more importantly, what we have learned from this observation is that even this distant star that has exploded 160,000 light years away is also made of atoms. And this star has been putting these atoms together to build up heavier and bigger elements all along.